our final talk of the session, which is from Severin. Can you share your screen? Okay, so Severin will be telling us about the tadpole problem.
Okay, yeah, thank you very much. Thanks for the introduction. Can you all see my screen? Does that work?
Yes.
I guess. Yeah, so I should mention this is mainly about two upcoming papers with Josef Behner, Jan Blabak, and Marianne Granja, but also about three older papers with the following people in many different orders. But foremost, I'd like to thank the organizers, not only for giving me this last slot in this very nice conference, but also to organizing this conference as an online conference. And I was, of course, as many of you, already looking forward to seeing all of you live in Boston, but this turned out to be very nice, even in this format. And if I cheat by looking at the topics of the Slack discussion channels, we heard, roughly speaking, talks from the four following topics during this week. And what I would like to present here, I think very nicely fits into at least three of these topics. So let me start. And I think in front of this audience, I do not really have to tell you that in flux compactifications, you expect a huge landscape of different vacua, 10 to the 500, or in F theory, an even bigger number. I should apologize if I forgot any reference also for the following slides. And this vast number of vacua, roughly speaking, comes from, if you have a Calabi-Yau manifold with large Hodge numbers, you have many cycles and you have many possible choices to arrange fluxes on these cycles. But of course, these fluxes are constrained. Foremost, they have to satisfy some form of integer quantization law, and also they have to satisfy Tadpole cancellation. And the goal or the difficulty of this program is to find a consistent vacuum, ideally, which also stabilizes all the moduli within these constraints. And we have heard many talks before, which told us why this is difficult. I in particular also liked Jakob's talk before, who showed us a really nice method for achieving this goal. But here I would like to mention some potential issues which could maybe arise at a large number of such moduli. Maybe let us look at the Tadpole cancellation condition. In F theory, it takes the following form. It tells us that the D3 charge from the fluxes has to cancel off with the D3 charge of localized sources. In type 2b, the D3 charge of localized sources essentially comes from D3 branes, O3 planes, and D7 branes and O7 planes. And to allow for fluxes, we need some negative contribution, so we necessarily need some O3 planes or D7 branes or O7 planes. And all this can be very nicely encoded in a much more simple fashion in F theory in terms of this expression. This actually does not include the D3s anymore, but it contains on one side only the contribution from the fluxes, the free-form fluxes on the base manifold, and also the word volume fluxes on the 7 branes. And on the other hand, it only contains one simple topological number, namely the Euler number of the Calabi-Yau fourfold, and this encodes all the difficult D3 charges from the D7 and O7 brane sources in the type 2b limit. let us look at how we can express the Euler number in terms of the topological data, the Hodge numbers of a fourfold. This can be done by the following formula. And here, since we're talking about flux compactification, I mainly want to talk about, or I would like to spend my focus on the H31, the complex structure moduli of the moduli, and in particular, I will mostly assume that H11 is comparably small, that there's not too many Kähler moduli. If there are many Kähler moduli, we also have to do other things to stabilize Kähler moduli, but I do not want to talk about this. So from this, we see that the scaling with H31 of the Euler number divided by 24, as it appears in the Tadpole cancellation condition, scales roughly like the H31 divided by 4. And now we would like to make the following a bit speculative and maybe also provocative conjecture. What if the flux we need to stabilize all this moduli, and also to get a consistent vacuum also has a similar scaling behavior with the number of moduli, say that it is always larger than some number alpha, some order 1 number alpha times the number of complex structure moduli we want to stabilize. So this would imply that there are no vacua with large H31 if this number alpha is larger than 1/4. So we could in particular also ask if there's a strong version of this statement, maybe with alpha equals to exactly 1/4. Of course, this looks a little bit like a swampland constraint, even though it's slightly different in nature because it does not directly something formulated in a 4-dimensional effective field theory, but rather is a statement about the 10-dimensional compactification itself. But it would, if it is true, it would certainly constrain the landscape of string vacua. So for the rest of the talk, let me talk about the following two things. First, I would like to mention some particular application or implication of this conjecture, and in particular in the KKLT setup, the uplift to the zeta vacua with anti-D3 branes in a Klebanov-Strassler throat. And after that, I would like to discuss 2 examples where one sees a behavior like this. And first, it's a well-known example of D7 branes in type 2b. And the second example is M theory on particular 4-fold K3 times K3, where we use some computer search for vacua, and we'll see some structure like this arising. So let me first start with the application. So as you are aware of, in KKLT, we put anti-D3 branes in a warp-deformed conifold, a so-called Klebanov-Strassler throat, to uplift to a de Sitter vacuum with positive energy density. So this deformed conifold is described by its embedding into 4-dimensional complex space via the following equation. In particular, this S is the so-called deformation parameter. It corresponds to the size of a 3-sphere at the tip of the conifold, and therefore can be seen as a complex structure modulus of this geometry. And it also enters the warp factor of this geometry of this solution, and therefore controls the hierarchy, or if, as you wish, the length of the throat. And some time ago, in Douglas, Shelton, and Toroba, computed a potential for this modulus, which takes the following form. The important part is here to include the effects of the warping. It can be seen as a flux potential for this modulus S, and it's sketched here on the right-hand side. And so the blue line is actually the potential, including the warping. The dashed orange line is the potential as one would get it without the warping effects. And the interesting feature is that it has this bump and that it goes back to 0 for very small values of S. So we could ask what happens with this potential if we add a anti-brain to the throat. So we could compute the contribution to the potential of the anti-brain, and the energy, the contribution in energy to the anti-brain essentially is the tension of the anti-brain multiplied with the warp factor. There's a factor of Q coming either both from the dBi term of the anti-brain action and the Chern-Simons term. So essentially the contribution to the potential from the anti-brain scales like the warp factor. So it has this power law function in S. And if we add the two potentials, one gets a behavior as in this drawing there. And then depending on the amount of flux in the throat, we see that either there still remains a vacuum with positive energy density with positive cosmological constant, or depending on how steep the anti-brain potential compared to the flux potential is, there might also be a runaway behavior to a singular solution called a so-called Klebanov-Strassler throat with x equals to 0. And if you carefully compare these two potentials, you obtain the following bound on the square root of G string times m, where m is the amount of flux quanta on the throat, and it has to be larger than a certain value. For one anti-brain, the value is exactly, it's roughly 6.8, and only if you have enough flux on the throat, you see that the uplifting procedure is stable. So let me see. There's another piece of evidence for this particular physics in the anti-brain. So we could assume that we put a different form of positive supersymmetry energy density in the throat. For example, instead of an anti-brain, we could try to embed a black hole at the tip of the throat. And indeed, such kind of a black hole has numerically constructed by Alex Bushel some time ago. And he found that this black hole only exists if the energy density of the black hole is not too large. If one increases the energy density or the temperature of this black hole, one goes back to the Klebanov-Zeitling, the singular solution with S equals to 0. So it's kind of similar to the situation with the anti-brains. If the object at the tip of the throat is too heavy compared with the fluxes in the throat, it will destabilize the throat. And so we went ahead and expressed the energy density of the black hole in units of anti-brain energies. And we indeed found a very similar bound on the flux quanta in the throat. The functional form of the bound is exactly the same, only the numerical coefficient is slightly different. There's yet another way of looking at this configuration as figured out by Lisa Randall last December. So instead of looking at the full Klebanov-Strassler solution, the full 10-dimensional solution, we might want to use an effective 5-dimensional description as in an RS scenario, where we replace the bulk Calabi-Yau with a UV brain and the tip of the conifold, and possibly also the anti-brain with the IR brain. And then you can see that the Klebanov-Strassler modulus S, which we talked about before, essentially plays the role of the radiant field, which parameterizes the length of the throat, the distance between the two brains. And in the RS scenario, can be stabilized by so-called Goldberger-Weiss mechanism, which generates a potential for this radian, which generically is of the following form. And if we now look at the potential for S in the Klebanov-Strassler throat, this can be approximated to the following form. So it takes essentially the same form as the Goldberger-Weiss potential for the radiant in an RS scenario. And then adding an anti-brane, adding a positive energy density, essentially corresponds to a perturbation of the IR brane tension, which changes the stabilization in the Goldberger-Weiss mechanism. But I do not want to go too much into the details here. So let me conclude this section by making the connection to the before mentioned Tadpole conjecture. So in the Klebanov-Strassler throat in GKP or KKLT, the hierarchy is essentially described by the value of this field S, which takes a exponentially small or large value and is tuned by the ratio of the two fluxes K and M. And our result shows that G string times M square has to be larger than a certain value for this setup to be stable. But on the other hand, Tadpole constellation also constrains the product K times M. This has to be smaller than something we call the effective D3 charge, which is left over for the throat. So which is essentially the difference between all the localized charges and the D3 charges from all the other fluxes which are needed to stabilize the moduli of the Calabi-Yau bulk. And now we can use these two constraints, these two bounds to get a bound on the hierarchy. And if we insert these two bounds, we find that the hierarchy, which is essentially this H is a logarithm of the ratio of the two scales, is essentially bounded by some factor times this effective D3 charge, which is left over for the throat. So, and if we now go to F theory and assume that this Tadpole conjecture holds, this Q effective is essentially the Euler number of the Calabi-Yau minus the contribution from the fluxes on the bulk. So this is bounded by this quantity over here. So, and if a strong version of this Tadpole conjecture holds, if this factor alpha is equal or larger than 1/4, one sees that even with a large number of moduli, even with a Calabi-Yau with a large Euler number, one cannot obtain a large hierarchy. So let me now go over to the first example for a setup where something like this seems to happen. So this is taken from an old paper from these three gentlemen. So let me not go too much into the detail here. So they considered a elliptically fibered Calabi-Yau fourfold where the base manifold is just a CP3. So the elliptic fiber is described by this Weierstrass equation. And the topological data admits a Euler number, which is kind of large. So the contribution to the Tadpole constellation is 972. But this comes at the cost of almost 4,000 complex structure moduli. And if we go to the Sen limit, we expand the two polynomials f and g in the following form, where h, eta, and chi are polynomials of a certain degree, and the loci of D7 branes are then described by this polynomial equation. And to get the number of D7 moduli, one has to count the degrees of freedom which are left over in describing these polynomials, and one arrives at the following result. There are 3,728 D7 brane moduli. So one sees in particular that the vast majority of the moduli does not come from the complex structure moduli of the base manifold, but indeed comes from the D7 brane moduli, which are here encoded into the F theory geometry. So they went ahead and looked at this setup in type 2b. So here we describe the D7 branes, assuming they wrap some surface of degree 2m by a polynomial equation of the following form. And now one can do a similar counting, and one obtains that the number of moduli roughly scales like 4/3 times the third power of the degree m. And of course, in reality, one has to cancel the D7 tadpole, which tells us that m equals to 16. And then by plugging in m equals to 16, one obtains, of course, the right value, which is also predicted by F theory, this 3728. And now to stabilize all these moduli, one has to turn on world volume fluxes on this D7. They are dual to a certain curve on the world volume of these D7s of, say, a curve of degree d. And then one can count the number of constraints which arise due to these fluxes, and one arrives at the following quantity. And then to stabilize all the moduli, one has to demand that the number of constraints is larger than the number of D7 moduli. And then this gives the bound on the degree of the curve describing the fluxes on the D7 world volume. And one can finally compute the D3 charge coming from these fluxes. They're given by the following quantity. If we plug in our bound on this d coming from stabilization of all moduli, one sees that the D3 charge to stabilize all moduli has exactly the same scaling and also the same leading coefficient than the number of moduli themselves. So one sees indeed that the D3 charge needed to stabilize scales in the same, really scales with the number of moduli here. And in particular, if one plugs in the value of m equals to 16, one obtains that the QD3 has to be larger than the 3276, which is much larger than the available tadpole in this setup. So they already speculate back then in this setup that maybe in weakly coupled type 2b, here no D7 brane moduli stabilization is possible. So let me go over to another example of a slightly different kind, namely M theory on K3 times K3. This is actually a very well-studied example. Already Aspinwall and Kalosh managed to stabilize all complex structure moduli of the setup within the tadpole bound, and they also managed to stabilize all the Kähler moduli by other means. And also the Euler number of this setup is not particularly large, so why one might ask why it is interesting to ask. Moreover, it's a very peculiar Calabi-Yau fourfold. It's not a true generic Calabi-Yau fourfold. Nonetheless, it has a lot of very nice properties which make it very interesting for us to study. Namely, in 2008, Andreas Braun and collaborators found that in this setup, one can stabilize all the moduli, the Kähler moduli and the complex structure moduli by fluxes. And the very nice thing here is that we can stabilize moduli without explicit knowledge of the period maps. And we can do that at an explicit point in moduli space, which makes this very accessible for a very detailed analysis. So what we want to do here, we want to go back to the setup of K3 times K3, and we want to stabilize all moduli with fluxes. And in particular, we want to go to a generic point in moduli space. So we want to have a setup where the K3 times K3 does not develop a singularity, and we want to see if this is possible with arbitrary small tadpole, with arbitrary small Q3 D3 charge from fluxes, or if there arises some behavior as we speculated about before also in this case. I should mention that we do not really care here too much about the F-theory limit. We just want to stabilize moduli directly in M-theory and see what is the generic behavior of this setup. So let me remind you about a few features of the moduli space of K3, which is actually quite nice. So the integer middle cohomology is described by the following lattice, which contains two factors of E8 and then 3 factors of U, where U is a simple lattice of signature 1, 1, which is a unique even self-dual lattice of signature 3, 19. And then a point in moduli space can simply be characterized by a choice of 3 self-dual 3 forms in the middle cohomology. And then I can take two of these 3 forms to form the harmonic 2 form, and the third 3 form to form the Kähler form. So by this one uniquely specifies a point in the Calabi-Yau moduli space, and the choice of these three forms then kind of corresponds to a lattice to a 3-plane embedded in this 22-dimensional vector space as sketched over here. And in particular, sometimes one can orientate or rotate this 3-plane in such a way that it kind of locks in with the lattice, and that some of the lattice points it turns out to be exactly orthogonal to this 3-plane. And if such a lattice point is a root of the lattice, if it has a norm 2, this means that the K3 develops a orbifold singularity, and in particular the combined roots which become orthogonal to this 3-plane, they characterize this singularity. So one arrives at a simple ADE classification of these singularities just by looking at which roots are orthogonal to this 3-plane. So the very nice thing is we can just describe any point in by specifying one single 3-plane. So we can exploit this, which was done in this paper back then, to describe moduli stabilization on K3 times K3. So we take the 4-form flux in the following way in the middle cohomology of this manifold. And so it's just described by a 22 times 22 dimensional integer matrix. And using this matrix, we can define a map from one middle cohomology from the H2 of K3 onto itself. And then we can describe the whole business of moduli stabilization just in terms of this map. We can take this matrix N, which we form out of the flux matrix, and we can diagonalize it. And it turns out that the eigenvectors of this matrix N uniquely split into 3 eigenvectors with positive norm and 19 eigenvectors with negative norm. If this matrix N satisfies certain simple properties, it has to be diagonalizable with real and non-negative eigenvalues. And if it has degenerate eigenvalues, then the corresponding eigenspaces have to have a definite signature. And in this case, the 3 eigenvalues with positive norm uniquely characterize exactly a 3-plane, and this 3-plane is exactly the 3-plane specifying a point in K3 moduli space. So we can describe moduli stabilization just in terms of an integer matrix and in terms of its properties with respect to diagonalization and with respect to its eigenvalues and eigenvectors, which makes the whole procedure very simple. And in particular, also the tadpole is just given by the trace of this matrix. So the goal is to find such an integer matrix which has the desired diagonalization properties such that we obtain a Minkowski vacuum and such that all moduli are stabilized. And in particular, we demand that there is no root of the lattice which is orthogonal to the three positive norm eigenvectors of this matrix, which means that we demand that the K3 is smooth, that in other words, we are at a generic point in moduli space. And moreover, we want to demand that the trace of this matrix is minimal, which corresponds to the minimal tadpole, or in other words, to a minimal D3 charge by fluxes. And such a setup is perfectly suited for a computer search with the evolutionary algorithm. We already heard a lot in the talks yesterday, and I refer you for reference to these talks, and in particular also to Alex Cole's talk for applying genetic algorithms for finding flux vacua. So let me very shortly tell you what is the evolutionary algorithm, or what is differential evolution. This is the algorithm for solving optimization problems inspired by biological evolution, so by things like reproduction, mutation, and selection. So the goal is we have some search space R to the n, and we have a fitness function characterizing how good the solution is on this search space. And we want to optimize this fitness function. So we select, randomly initialize an initial population with capital N entries out of this search space. And then for each element of this search space, we randomly select two other elements, form their difference, and modify the element by this difference. Then we obtain some x prime by this procedure. Then we randomly combine our original x and the x prime into some x double prime. And then if this x double prime happens to be fitter than the original x, we replace x with x double prime. And we repeat this procedure over and over again. So we obtain a population which after each iteration is hopefully fitter than before. And this hopefully allows us to find a global minimum of this optimization problem. So we went ahead and implemented this for our problem in the Julia programming language, using a package called Black Box Optimization and a very nice script which Johann Blabak wrote. But even though we are dealing with a problem which in principle looks kind of simple, with just the integer matrix and some properties of this integer matrix, it turned out not to be as simple as we originally thought. So one problem is that this is really a huge search space. We have a 22 times 22 dimensional search space. For example, if you just focus on integer matrices with entries 0 and plus minus 1, you already have 10 to the 231 configurations, which is a huge space. And moreover, we want to demand that we only look at non-singular K3s, so that there's no roots orthogonal to the three positive norm eigenvectors. And it is known in computer science that this is the NP problem. So it's a very difficult problem we have to solve in actually every iteration in the evolutionary search. There's also a lot of mathematics and interesting stuff going on there, and we spend a lot of time in trying to find a solution to the second step, but unfortunately I don't have any time to talk about this. But due to these difficulties, the search, even though it works quite nicely, it converges very slowly. It often takes multiple weeks for us to find a result. For example, after 1 to 2 weeks runtime, we find a solution with a tadpole of T equals to 24, so a flux configuration with a flux D3 charge of roughly 24. We still have to check if this solution is really completely smooth. There might be still some issues with the roots orthogonal to the positive norm eigenvectors. But it's kind of difficult to say if this is already the minimal value we can possibly find. Assuming we let it run not only 1 to 2 weeks or 1 to 2 months, maybe can we find a tadpole 23, 22, etc. So it's very difficult to decide when or if a minimal T is found. In other words, by such a procedure, we can never really find a proof for the non-existence of such a vacuum. We can always only show the existence of a certain vacuum if we find it, but we will never be able to give a proof for the non-existence of such a thing. So we kind of changed strategy and looked at smaller lattices. So we looked at matrices, lattices of a much smaller dimension. And here the thing converges rather quickly. It rather quickly converges to T equals to D, where D is the dimension of the lattice. And even after a very long search, no smaller tadpoles can be found. So from this, we conclude that the minimal tadpole is always more or less equal than the dimension of the lattice. Here's a plot of the convergence of the search over time. So after roughly, so this is for 2 hours. So after roughly 20 minutes, already the smallest possible tadpole is found. But after that, we can let it sit for almost as long as we want, and it will not go down further. So here's another illustration of the thing. So if we look, for example, at the 6-dimensional lattice and we make a snapshot every 120 seconds, we see that after a while, the whole, so this is plotting the tadpoles found in the population, that after a while, almost all matrices arrived at the minimal tadpole of T equals to 6, but none of them is going below. So from that, we conclude that the minimal tadpole is almost given by the dimension of the lattice. Sometimes we also find, for some lattices, we find that the minimal tadpole seems to given by the dimension of the lattice -1. So we still have to do a little bit of work here, but it seems to be pretty robust. So if we can extrapolate this to the K3 lattice, and if we assume that this also holds for the full 22-dimensional lattice, then we see for M theory on K3 times K3, the following 3 properties. We cannot have all of them at the same time. We cannot have stabilization of all moduli, generic point in modular space, so no orbifold singularity, and fluxes with an arbitrary small charge at the same time. So we always have to sacrifice one. So if we want to have fluxes with a very small charge, we either need not stabilized moduli, or we need a singularity or orbifold singularity, which then would give rise to a gauge group. So in this case, we always see some additional light degrees of freedoms. And it would, of course, be very interesting to explore this further. For example, we could allow for a very small singularity, a small gauge group, how much we can lower the tadpole in this case. So thank you very much.
Okay, thank you. We have time for a few short questions. Yes, we have a question from Bruno Colecto Bento.
Hello, nice talk, Severin. I have a question about the hierarchy, about your results from the previous paper. What sets the hierarchy in the KKLT setup? What kind of hierarchy are we looking for?
What I'm essentially looking at is the hierarchy, the difference in warping between the ratio between the warp factor and the UV Calabi-Yau at the tip of the conifold. And essentially, the warp factor is given by this thing here, which contains this S. This hierarchy is controlled by this modulus S.
But in terms of magnitude, what constrains the magnitude that the hierarchy that we are looking for?
I believe in the original KKT paper, this variable h, as we call it, has to be something like order 10 to 20, which would mean Tadpole Q effective of, I think, something around 400, for example. But it is, of course, possible to play with numbers. I don't know what you really strictly need there to make it work in KKT.
Right, thank you.
Okay, I saw a raised hand from Arthur Hebecker first, so can we go to your question?
Yes, thank you. So if you have unstabilized moduli, as long as these are D-brane moduli, maybe that's really not that bad, because you just have light fields which will get stabilized by the SUSY breaking scale or alpha prime correction or something. You see, it doesn't necessarily destabilize because their field space is compact. So I'm just saying you may have an interesting prediction, but not necessarily a problem for the whole setup.
Yeah, okay. I mean, this could be if you say that some of these moduli are fine, and if it is particular the D7 brane moduli, which often seem to be the one which are most troublesome, then from a phenomenological point of view, this still might be fine. Yes, yeah. Still, I think there's some interesting physics going on also, as we saw.
Yeah, I totally agree. I want to emphasize it may be an interesting prediction for cosmology. I mean, many relatively light fields is interesting.
Yeah.
Let's see. I see a comment just came up from Lisa Randall, which is related to that. So Lisa, did you want to say something?
There's two things. I mean, one is just that the whole point of this construction was to show that there definitely is a solution. So you might well be right that there's a solution, but until we actually show it, then we don't actually have this explicit example yet. But of course, it's worth doing. That was a comment.
Okay. Our next question was from Cameron Baffa.
Thank you. So very nice talk, Severin. I have a question. The structure of the stabilization of the moduli that you worked out for the K3 times K3 case has a number theoretic kind of fixed point, somewhat analogous to complex multiplication points that one sees in elliptic curves. Have you tried to study the same question for more general Calabi-Yau four-poles and whether there's an interesting structure or general question of can we reformulate this in terms of some number theory type question in general?
So we did not study it for Calabi-Yau four-folds, even though this is certainly somehow on the bucket list. We kind of started looking at it for this very particular example of K3 times K3, and already at this question on trying to see whether they can be roots orthogonal to the 3-plane or not. You pretty quickly run into similar number theoretical structures like complex multiplication, etc. So I mean, in general, you have this 22 by 22 dimensional matrix which has 22 complicated real eigenvectors, and usually none of them have a linear combination which can be an integer vector. But I mean, sometimes if and the eigenvalues are characterized by the characteristic polynomial of this matrix, but sometimes this characteristic polynomial is reducible of the integers, and these are exactly the cases where singularities arise. So there's also some related properties related to certain algebraic number fields bound by the eigenvalues of the corresponding characteristic polynomial, etc. So we started looking into that, but I cannot say much on it, unfortunately.
Okay, thank
Okay,
you.
Jim Halverson has a comment and a question, he says.
Hi, Severin, very nice talk. So just a quick comment and a question. The first is just in general. So it turns out that Sen limits almost never exist. So in known ensembles of F-theory geometries, Cody had a result a few years ago that the probability of having a Sen limit is like below 10 to the minus 300. So it's super rare. So that's a caveat. And so you chose to study this case where you had an elliptic vibration on P3 a la Colanucci, Denef, and company. So another thing is that P3 is a particularly, it's an example that can lead to huge sample bias. So I know it from personal experience that it's a very, very special example with respect to 7-ring moduli. There's tons of them. So my question is, there is an ensemble where you can guarantee the existence of a Sen limit and are not going to have some of the same problems that are P3. These are the F-theory bases associated with 3-dimensional reflexive polytopes. There's like 10 to the 15 of them. There's, all of them have a Sen limit, etc. Have you guys thought about trying to broaden out beyond that one example at all?
No, we certainly did not do a systematic survey of all of them, even though it would be very interesting in this context to do this.
Yeah, I mean, it's a very, I mention it because it's a very tractable analysis to do. It's actually pretty easy. And in particular, the issues that P3 has, looking a little more broadly, if you were making a wrong conclusion in the P3 case that doesn't hold more generally, that would help you avoid it. And it's just very tractable. So
I agree. This would be very interesting to do. Yeah. I mean, the appeal of the K3 thing, even though it is certainly not a generic Calabi-Yau fourfold, is that we can do a very general analysis. And as I said, we have these properties of looking at a generic point and moduli space.
Exactly.
It's very difficult. So this seems to be, and our analysis seems to indicate that looking at a generic point and moduli space has different physics than allowing to go to a singular special point and moduli space.
That's absolutely right. And so, for example, the place where you can draw a wrong conclusion is there's this result of Brown and Latari from like 5 or 10 years ago, where they basically said, let's tune some gauge symmetry on a hyperplane in P3. And what they found was that relative to the generic point and moduli space that you guys are studying, you have to turn off like 1,000 moduli or more to get SU5 or SO10 gauge symmetry. And so for a while, there was this idea floating around in the community that that was going to be something generic. And in fact, that was very specific to those examples. So it's a case where you basically, if you only study that one example, I know it because I felt the pain, you draw a wrong conclusion. So these other cases, you can study generic points in the moduli space too. So that's it.
I see. Yeah, this certainly would be very interesting. I agree.
All right, thanks.
Okay, so let's do the one last question and then we'll move on to Fernando for our after dinner talk. So we had a question from Dibya Chakraborty. Is the tadpole conjecture only valid for Calabi-Yau fourfolds or can it be generalized to other n-folds?
I don't know. I mean, ideally, I would think it should also hold for other n-fold. If it holds, I hope it would hold for also for other n-folds, yeah.
Okay. Okay, so if there are no remaining quick comments or questions, let's thank Severin again and thank all of our speakers for today.
Thank you.
Let's see, I see a comment just popped up from Arthur. Is this something you want to say out loud or is just writing it in chat good enough?
Sorry, that was just an answer to the comment. We are chatting with Lisa, sorry. It's fine. It's not so important.
Okay, so so then let's move on to Fernando Quevedo,